Okay, so I'm just filling the data with sound so that I can get my feedback and I know that everything's working. I got my notification, so that's good. Let's see, testing. Okay. So that's working. I'm gonna go ahead and close that. Go ahead and close that. Let's get done. Who is this? Let me get this student. Oh. Yeah, let him in. And share the screen. And we'll start here. Ooh, all right. Here today. Okay. So yeah, sorry about the background noise. You know, we just have to do the best that we can with what we have. Let me see. All right, gentlemen. So welcome back. Right. So I feel like we definitely need to have a quick little powwow. So I calculated midterm grades. I submitted them yesterday. So those should be available on Bannerweb. So you want to check it out. If you are seeing grades that you do not like, I want you to know that like there's still time to turn this thing around, right? You just got to do something different. Either link up with me as best you can, link up with your classmates, and link up with the tutors. That combo, as long as you push and work hard and actually make a genuine effort, you can honestly get whatever grade you want. And it's not too late for any assignment. Remember? So just as a friendly reminder, you know, with all of our assignments, you get unlimited attempts, and you can work on any assignment past the due date, right? So everything that we have, you can actually work on it past the due date. You can work on it right now. You know, you can sit down with whoever you need to sit down and just get through it, right? You've paid for the tutors; they're part of your tuition, so you've already paid. You just need to access them and you know, use your resources. You know, if you don't use them, then you're just giving them your money, and you know, you're just throwing your money away. Yeah, that's the main thing, right? If your grades are where you like, then just kind of keep doing what you're doing and just try to help as many people as you can. Right? It's okay, just get it done. If you do want to talk about your grade, or basically what I did for the grades, I made like the homework worth 10%. I think the quizzes were worth 10%, and then any exams that we taken, I took their average, and that was worth 10%. And I just pulled it pretty much straight from Pearson, right? And so if it looks wrong, or if you calculated something different, again, I took the average of your homework and then said times 0.1, so that's 10% of your grade. The quizzes, I took the average of your quizzes and then said times 10%. And then I took the average of your exams that we've taken and I said times 0.8 because it's 80% of your grade. Let me think. You can improve any score that's there. There was something else I was trying to get out. It'll come to a little bit later. Okay. Yeah, and so, you know, I generally, you know, anything can happen. I've seen where students were at the bottom, you know, of this experience, and then they were able to turn it around and pull through and keep it moving. Rarely, I don't think that ever, like very, very rarely are students at the top and then they just fall off. That doesn't happen that often. But you know, anything can happen, right, at this moment in time. So I can't think of the other thing that I wanted to mention. Whenever it comes back, I'll mention it as best I can. Yeah, but it's a good idea to, you know, just look at your grades. You want to see your midterm grades. And yeah, I guess the other thing I wanted to say was that, you know, the midterm grade, all it is, it's just a snapshot of where you are in that moment in time, right? That's all it is. It's just a snapshot. It doesn't dictate anything. Even your final grade doesn't dictate anything. That's just where you finish at that moment in time. That was has a little bit different consequences, but honestly, you know, don't get me started on the philosophy of this, okay? Because I feel like it's all a scam anyway. Not a scam, that's not the right connotation, but for instance, and this is a little side note, but I was watching this like presentation this morning on YouTube by this gentleman that goes by the name, his channel is about minority mindset. He's always talking about like financial literacy and all this stuff, but it's just really interesting, right? And he makes a good point in that we don't really talk about finances in school. It's not promoted. Why? Because it needs to be. If we live in a capitalistic society, we need to talk about this stuff, right? So that people can live. And so, like in the presentation I saw today, he talked about three main tracks to wealth, right? And on the far right, he had like lottery was one of them. And then in the middle, he talked about like basically labor, where you make an hourly wage, and that's what's kind of promoted in like school and everything like this. But then the other track, he was like, hey, we live in a capitalist society. So the first one was capitalism, like being a capitalist, an entrepreneur. And basically he was like learning how to make it so that your money makes money for you, right? But we don't really talk about it. So I do my own research, and it's really interesting. I think he makes good points. But how do you build the capital if you don't have the capital to play the game, right? And so a lot of times we don't play the game because we don't know the rules. It was just stuff like that. It was really interesting. So that's why I said that, because again, even if your final grade was not desirable, where there's always a way to get something done. You always have to just, if you're talking to somebody and they're not saying what you wanted to hear, more than likely you're talking to the wrong person. You just got to talk to somebody else, or you got to change your thinking or try something different. You can't keep doing the same thing and expect a different result. That's the definition of insanity. If you want something different, you got to think different. You got to act different and be different. You know what I mean? You got to become the change you want to see. So, okay, I feel like that's enough of like a little bit of cracking the whip and a little bit of motivation to get on the soapbox. And so, with that, we're kind of, I don't want to be like we're in a home stretch, but there's not that much left. I was kind of glancing ahead right before we started. So this is what, week 9 or something like that, 10, maybe 10. But we're going to do, we have our 3 weeks of lecture. So we're going to be starting chapter 6 on sequences and series. So we got 6-1, 6-2, and 6-3. Then we take exam 3 over those 3 sections. And then we have one more section after that, right? And I don't know if I'm going to do this next thing that I'm going to share, but I want to put it out there and just see what happens, right? So I was thinking like, okay, for the last 2 weeks, maybe for the last 4 lectures, the last 4 times that we meet before the final, I was considering like, okay, let's take this stuff that we've been talking about and see, can we bring it alive, right? Like, because I consider myself a gamer, can we apply it to gaming or construction? I do origami. So I was like, well, maybe we can like take some of this stuff and see what are some of the ways that we can bring it in our lives. We are aware that there are like applications that, they might seem a little bit disconnected from us, like programming or this, that, and the other. But I wanted to see if we can like take this information that we've been talking about and bring it alive to things that are relevant to us. So I know, again, I can't speak for you all. I don't know what's relevant for you. I don't know what's relevant for you unless you say it. But I know I'm like always a YouTube researcher, and I was even thinking about changing my presentation style. I was thinking about getting a green screen and like, okay, maybe I'll show my image, and then like I'll show my image with an iPad behind me. Like I think I can do it. So it's like I'm going to be in a virtual reality. It's like film and production. Like I got these ideas. I have a lot of them. I need like an intro and outro, music. Any kind of way to bring something we've been talking about alive, bring it alive in a way that's relevant to us, right? So that's what I was thinking about. So we'll see. We'll revisit this as we get closer, like at least after exam 3, right? I know there's one more section. I might just do that one asynchronously and then point you toward it, and then we can take. I really want to take those last 4 lectures as an opportunity to just explore and see how we can bring this information alive. Let me check attendance one more time before we're looking good. Okay, I guess you guys can hear me. Let's just kind of get the party started, right? And so the goal for today, we're going to go ahead and start chapter 6 on a few further topics in algebra. And today we're going to be working on section 6.1, sequences and series. And so it's an average of a fair amount of slides. So my goal, I'm going to go ahead and start going through this lecture. I'm basically doing a live lecture. If we don't finish by the end of class, I'll release you all, let you go early. You're welcome to stay, but I'm gonna keep going until I finish this section, right? But once we hit that time, I mean, obviously, we're doing remote asynchronous anyway. You can leave once you get your attendance ready. You're not obligated to stay. But I would hope that you would have stopped in what I'm sharing. You know, I would imagine, but again, I acknowledge that life happens, and you know, I acknowledge certain things, so it's okay. You know, so with that, I'm gonna. I think this is okay. I think that's fine. Okay. So we're gonna go ahead and move into section 6.1, sequences and series. And again, as always, if anything is not clear or if you want to talk, if you have questions, comments, or concerns, you just have to unmute yourself and make your presence known and get my attention and we can talk about it. If you feel like it's something that needs to be private, just kind of stop me kind of closer towards the end. I can stop the stream if needed and we can talk like in a private one-on-one room or whatever. Okay. So we have section 6.1, sequences and series, and a few objectives. We like to use sequence notation and find specific and general terms in a sequence. We like to use factorial notation and use summation notation to write partial sums of the series. Okay. So definition of a sequence: an infinite sequence is a function whose domain is a set of positive integers. The function value is written as, you know, a sub 1, a sub 2, up to a sub n and beyond are called the terms of the sequence. The nth term, an, is called the general term of the sequence. So the sequence is just going to be like a list of numbers. Okay, let's keep going. So in this example, we're asked to write the first 4 terms of the sequence defined by this. Okay. So the first 4 terms, right? So for instance, when n is 1, so then b sub 1, we're just replacing all the n's with 1, is going to be -1 to the power of 1 plus 1 times 1 over, right? So 1 plus 1 is 2. -1 squared is +1. Ultimately, the first term is 1. So let's look at B2, the second. He's going to do the same thing. And all that we are doing is making this guy and this guy those are the things that we're changing. And actually, let's undo. Okay. And this next one is essentially the same thing. So now we change all those 1s to 2s. So then B2 is going to be -1 to the power of 2 plus 1 over times 1 over 2, right? So then 2 plus 1 is 3. -1 to the power of 3 is a -1, so that remains -1 times a half. So then ultimately we get -1/2 for that term. Okay. I think I get one more in there. Then the third term, 3 plus 1 over 3 plus 1, -1 to the power of 3 plus 1 times 1, 3. So then 3 plus 1 is 4. A negative number to an even power is going to be positive. So the net final result is 1/3. All right, so what I'm going to do here, I guess I get rid of this guy. I'm going to resize it momentarily. I'm going to bring that back in just a moment. So now we're doing B4 for F. So B4, 4 plus 1, 1 over 4. So then that's an odd power. So then the final result there should be a -1 over 4. Right? So let me see if I can resize these to the same size. I think we'll put these side by side. Enjoyed the spring break, had a good spring break, was able to do all the things that they needed to do, rest, get caught up on some work, whatever it is that you needed to do, hopefully you were able to do it, right? So that's what we got for the first term, second term, third term, and fourth term, right? And then let's do this. Let's do one more thing. So then the first four terms, we get what? 1, we got a half, then we got a third, we got a -1/4. So look at that. 1, -1/2, 1/3, -1/4. Okay. All right, let's try that. Here we ask to write the general term an for a sequence whose first 5 terms are given. All right. Okay. So we're looking at this. First term. Thank you. This is our first term. This is the second term, third, fourth, and fifth. Right. What can anybody notice a correlation with these terms and what the actual number is? You see anything? All right. So it looks like, for instance, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is so on and so on. So it looks like what we're doing is taking each term and we're basically squaring it. So for instance, A1 is going to be 1 squared, A2 is going to be 2 squared, so on and so on. All right, so that's what we get there. I can't wait to articulate that. Okay, let's try another one, right? Let's do something similar. So with this other sequence, again, just being a list of numbers, this is our first term, second term, third term, fourth term, fifth term, right? Again, can you notice anything? Now with that first one, maybe it might not be so obvious, right? But can you notice something? What do you notice? What do you notice, right? With each term. So notice you got, this is the second term, there's a 2 right there. This is the third term, there's a 3 right there. This is a fourth term, there's a 4 right there, so on and so on, right? And then also notice that the signs are alternating. It went, well, I guess no sign, then went positive, negative, right? So to capture that, we might do something like the following. So each term, let me see, it looks like we have 1 over that term, right? So if we're doing the first term, we have something over n. Now, if n is 1, the numerator is 1 less than. So we can say this is going to be n minus 1, right? And then notice we said that the signs are alternating. So usually whenever you have alternating signs like that, it's -1 to some power. If we did -1 to the power of n, let's see, if n is 1, right, that would be -0/1, which is 0. That one checks out. If n is 2, it's going to be positive. If n is 3, it's negative, right? I feel good about this. So then I think we can go with this. So again, like usually when you have alternating signs like that, it's -1 to some power, right? And then you just kind of keep playing and going back and forth until you get a general term that works for each one. We got n squared and then that one. Write the position number of the term above each term of the sequence and look for a pattern that connects the term to the position number of the term, right? And that's exactly what we did. So we had the term and we had the position number. The apparent pattern, 1 squared, 2 squared, 3 squared, so on and so on. We got that one. And then this one, when the terms align in sign and n is 1, we use factors such as -1 to the power of n if we want to begin with the factor of -1. This is fine. About the alternating signs. And then notice that each term can be written as a quotient with the denominator equal to the position number and the numerator equal to 1 less than the position, right? So I think we got that one as well. Okay. Let me just take a quick moment to check Zoom to see if we have any stragglers. Oh, we don't have stragglers. Let me check the chat real quick. So recursive formulas. So recursive formula requires that one or more of the first few terms of the sequence be specified and all other terms be defined in relation to the previously defined terms. So basically the sequence is like the first couple of terms are defined, and then the remaining terms are based on those first couple of terms, right? They're produced from those. The Fibonacci sequence is a famous sequence that is defined recursively and shows up often in nature. In this sequence, we specify the first two terms as A0 is 1 and A1 is 1. Each subsequent term is the sum of the two terms immediately preceding it, right? The Fibonacci sequence is like, I think it's like the Fibonacci sequence and the golden ratio. You can find it in the human body. It's all in nature, and it's kind of, it's interesting. It's spookily interesting, but eerily interesting, right? Like for instance, and you can't see it in my hand, I probably could draw a quick picture, but if you look at your finger and you bend it, right, and you have that first knuckle, like you have your fingernail and then the first knuckle, like the ratio between that joint and the tip of your finger, let me see, like if you compare the ratio of that length to the length of the second knuckle and the tip of your finger, is the same as the ratio between that length to the ratio of your entire finger, but then that ratio is the same as the length of that one compared to the length of your hand to the tip of your finger. Like if you just do a quick YouTube search on like the golden mean, golden ratio of the Fibonacci sequence in nature, it's a lot of like, it's everywhere in our bodies, rhythms, so many different structures, plant patterns, bug patterns, like it's everywhere. You're like, yo, and it still kind of points to this notion that we might be in a simulation. It's kind of spooky. It's really like trippy when you start seeing it everywhere. Like when you start to crunch numbers and how close this stuff is and how much of a pattern, even though it looks like, chaotic and random, but there are so many patterns that we're surrounded by. It just in nature, just the way things naturally are. It's spooky. When you look at like the spiral of a seashell, starfish patterns. I mean, it's so many places like where this sequence pops up. It's really interesting. Okay, so the Fibonacci sequence, right? So for instance, our first term, let me see. The first term was 1, second term was 1. So then A3, let's see. A2 should be, there it is. So then A2, right? So we're given A0 and A1. So then A2 is going to be the first two added together. So 1 plus 1 is 2, right? So then to get to A3, we got to consider A1 plus A2. So that's going to give us 3. A4 is 2 plus 3 to give us 5. And then 3 plus 5 to give us 8, so on and so on and so on. So this sequence can also be defined in the subscript notation. So then the first term was 1, second term was 1. And then, so each subsequent term, so there's going to be basically 2 terms ago plus the previous term, right? So basically the sum of the previous 2 terms for all k greater than or equal to 2, right? So this is a way to generalize that recursive sequence that we just experienced, right? So write the first 5 terms of the recursively defined sequence. Let's see. So they give us the first term and they tell us how to get to each subsequent term. Let me think about this. Okay, so they gave us, I must need to charge my case. I was like, how is that so little? The first term is 4. And then a sub 2, let's do it here. A sub 2 is going to be 2 times a sub 1 minus 9. So then that's going to be 2 times 4 minus 9, negative. So then if we want a sub 3, that's going to be 2 times negative 1 minus 9. Negative 11 minus 9. Negative 22, negative 31. Two times negative 31 minus 9. Negative 62, negative 71. Okay. So we get 4, negative 11, negative 1, negative 11, negative 31, and negative 71. Okay, let's see, how do we do? 4, negative 1, negative 71. So the first 5 terms of the sequence are these guys. So then a factorial. What do we mean by factorial, right? So for any positive integer n, in factorial, again, it looks like they're screaming n, but that's not what they're doing, obviously, right? So this exclamation mark, it has a meaning here. So this is called factorial. And what this means, in factorial just means, like for instance, if this was 3 factorial, it would be 3 times 2 times 1, right? Until you get all, you just basically, you take that number, you multiply by the previous number, and then times the previous number, and then you keep going until you get all the way down to 1. And then a special case of factorial is going to be 0 factorial. By definition, we just define 0 factorial to be 1. For instance, if we did 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So factorial just means take that number, multiply by the previous, and keep multiplying by the previous until you get all the way down to 1. And then again, a special case, when we do 0 factorial, that by definition is 1. So then we actually simplify these. Okay. So then for part A, 16 factorial would be what? 16 times 15 times 14 until you get all the way down to 1, all right? 14 factorial would be 14 times 13 until you get all the way. So we got 14 factorial. On top, if we're doing 14 times 13 times 12 until you get all the way down to 1, that's actually just 14 factorial. So then a number divided by itself, they cancel, is 1. So then ultimately, this is just going to be 16 times 15. Hey, Google, what's 16 times 15?
To play your favorite live radio station too. Just think, for example.
Oh my goodness. Thank you. Like she launches into this monologue. I was like, I just wanted to product, please. Please, thank you. Okay, let's try this next one. All right. So then part B. So maybe we can do something similar. So if we're doing n plus 1 factorial, all right? So that means we start with n plus 1 times the previous one is going to be n. All right, okay. Hang on, give me just a moment. Switch these out. So if we started with n plus 1, then the previous one, if we subtract 1, is going to be n. And then the next one is going to be n minus 1. And we can keep going until we went to 1, but that's essentially n minus 1 factorial over n minus 1 factorial, right? So then at this point, a number divided by itself, they cancel. We'll have n squared plus n, or becomes n plus 1. 40 and left with n times n plus 1. Here, we're asked to write the first 5 terms of the sequence whose general term is this, okay? So the first 5. Okay, so then that means that A1 is going to be negative 1 to the power of 1 plus 1 over 1 factorial. That's squared on top, so that's a positive 1. 1 factorial is 1, so then that's just 1. A2 is 1 to the power of 2 plus 1 over 2 factorial. It's going to be a negative 1. negative here. That's going to be negative 1 to the power of 3 plus 1 over 3 factorial. So that's an even exponent, so that's going to be a positive result. 3 factorial is 3 times 2 times 1, so that's 6. So that's for 6. 4. Negative 1 to the power of 4 plus 1 over 4 factorial. 4. To the power of 5 plus 1 over 5 factorial. Positive, it's the even exponent, and 5 times 24. 5 times 20 is 100, 120. Just a little bit, give myself some space. Don't be too hard. So do your best, but get the rest. Don't stress and be blessed. So the first 5 terms that we get 1, a negative 1. 4, and then we get 20. Shrinking. Okay, so I don't want to keep you all. Let me get rid of this. I don't want to keep you all past this point. I still have a few more slides. I'm going to keep going, but if you need to go, you're more than welcome to go. Just as a quick recap or overview. Again, midterm grades are posted. I probably do need to load them in Blackboard. They're not in Blackboard, they're on Bannerweb. If you need to see those details, we can talk about it. You just want to check it, make sure everything is in order. If it looks out of order, you just want to follow up to make sure that everything is in order. Otherwise, gentlemen, enjoy the rest of your day, and I will see you again on Wednesday. I'm going to kind of keep going and finish up this section. Okay, guys, take care. Peace. All right. So to keep going, we have a few more slides, a little over 10. So summation notation. It says the sum of the first n terms of a sequence is denoted by this, right? So let me see. The sum of the first n terms of a sequence A1, A2, A3, AN, right? And so on, is denoted by, now this is red, the sum as I goes from 1 to n of a sub I is going to be, so basically we let I be 1 plus when I is 2 plus when I is 3 up until whatever that value of n is, right? So this is the Greek letter sigma, right? Like in the Greeks, like fraternities, right? But in this context, this just means sum. So add up the sequences, add up your terms, right? So we're still doing sequences, but now we're adding up each term. So the letter I in the summation notation is called the index of summation. N is called the upper limit, and 1 is called the lower limit of the summation. Okay. So let's take a look at this. Find each sum. So then for part A, we have what? The sum as I goes from 1 to 9 of I is going to be, so first you let I be 1, so that's going to be a 1 plus when I is 2, 3. I'm going to abbreviate it until I is 9, right? You just add those up. Let me see. 1 plus 2 is 3. Let me write it up. Yeah, let's just write it out. So 3, 4, 5, 6, 7, 8, and 9. Okay. So then let's see. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. That puts it at what? 21, 28, 36, 46, 45, right? So these should add up to 45. Put the 45 over here. Okay. So then part B. So we're going to be doing the sum. Oh, and happy belated Pi Day, everybody. All right. Today is the 16th. So Monday was Pi Day, 3.14. I don't know if you guys played Dokkan Battle. Apparently, I can't think of it, but there's some aspect of the Saiyans. It's like 316 in Japanese, something like that. So like this is, I think today is Saiyan Day on Dragon Ball Z. All right. Anyway, that's just a side note. That's a random thing. Okay. Let's try to finish this up. So we have the sum, and actually, that's okay. I'm gonna just practice one drawing. So we have the sum as j goes from 4 to 7. We have this 2j squared minus 1, okay? So then we do when j is 4. So that's going to be 2 times 4 squared minus 1, all right, whatever that result is, plus 2 times 5 squared minus 1, plus, let me see, 5, 6, 7, 2 more. 2 times 6 squared minus 1. And let's put these in parentheses like this, so they don't run together so much. Plus 2 times 7 squared minus 1. All right, we're just basically adding up those terms. 4 squared, now you have to do order of operations properly here. 4 squared is what? 16 times 2 is 32, so then that's 31. Plus 25 times 2 is 50, so then that's a 49. Plus 36 times 2 is what? 72, minus 1 is 71. Plus 49 times 2 is what? 98. Minus 1, 97. So then, what is that? Let me see. So 30 plus 40 is 70, and 70 and 70 is 140. 140, 240, 230, 230, 240, 241, 248, right? It should be 248 if we did it proper. So I'm gonna check it with Google. Hey Google, what's 31 plus 49 plus 71 plus 97? Okay, I'll go with it. So let me get a copy of C, and I need to add a page, or maybe let me just shrink it down like I did the other one. And I'll resize it when I'm done to put it back, to expand it. So then for part C, we have the sum as k goes from 0 to 4. We got this 2 to the power of k over k factorial, right? So when k is 0, it's going to be 2 to the power of 0 over 0 factorial, plus when k is 1, 2 to the 1 over 1 factorial, plus when k is what? 2, so 2 squared over 2 factorial, plus 2 cubed over 3 factorial, plus 2 to the 4 over 4 factorial, okay? So then that's going to be 2 to the 0 is 1. 0 factorial by definition is 1, so that first term is 1. 2 over 1 is 2. 4 over 2 is 2. 8 over 6. 8 over 6, 4 over 3. Okay. 16 over 24. 16 over 24 is the same as what? 4/6, which is 2/3. I feel like I did something wrong. 2/3. Let me see. 8/6 is 4/3. 8 times 2 is 16. 16/24. Yeah, I feel okay with this. So then 2 plus 2 is 4, plus 1 is 5. So then we have 5/1. So then 15/3, 19/3, 21/3, which is 7. Looks like this adds up to 7. Okay. So I did a little bit of mental math. I probably would have been better off if I wrote stuff out. Let me see. Hey, Google, what's 1 plus 2 plus 2 plus 4/3 plus 2/3? That's right. Just give me the answer. That's all that I want. Okay. Let me resize all this to match them. Just kind of eyeballing it. That's decent, I guess. That's good. And then I'm just gonna expand it as much as I can. Okay. So we got 45, 248, and 7. So you see the 45 there. See the 248. You see the 7. Okay. All right. Okay, so hopefully that made sense. We're almost there. Just keep holding on. So then we have summation properties. So let A sub k and B sub k represent the general form. Go ahead.
Could you go back to that?
Mm-hmm. Which part?
Yeah, I just wanted to see that because you had that mental math when you did the last problem.
You see it?
Yes, sir, I got it. Thank you.
Okay, that's good. All right, let's see. So let A sub k and B sub k represent the general terms of two sequences, and let C represent any real number. So these are some summation properties, right? So if we say C times N, so the summation of a constant, right? So notice that in this summation there's no K. So we're gonna have N terms, but if you say like C plus C plus C plus C plus C N times, that's the same as C times N, right? So we're adding up something N times, but there's no K there, so it's just gonna be C times N. For instance, if N were like 3 and C were 4, then that would be what? 4, 1, 2, 3. So it'd just be 4 plus 4 plus 4, which is the same as 3 times 4, right? Yeah, I think that's it, right? So then this one, again, K goes from 1 to N. We have K terms, and we have a constant times each of those terms. We can actually factor out that constant. If we were to write the summation out, we would have C times the first term plus C times the second term plus C times each term until we get to N terms. Since all of those terms have been multiplied by C, we can actually factor out that C and move it to the front, all right? Because each term is going to be multiplied by C. So we can reverse distribute and factor, okay? So the sum of two sequences, we can break it into the sum of two series, all right? So we have this sequence plus this sequence, the sum of two sequences, we can break it into two separate sums. The sum of a difference of sequences, we can break into the difference of sums. So the difference of sequences, the sum of the difference of sequences is going to be the difference of two sums. The sum of the sum of sequences is going to be the sum of two sums. I know that's a little bit like nasty the way I'm saying it, but I think you can see it, right? We're adding these two things together, we can break them apart into two summations. We're subtracting these two sequences, we can break them apart into the difference of two summations. Let me see here. Okay, so in this series, K goes from 1 to N of, this general term. So then there's some j between 1 and n, right? So if we consider some j that's between 1 and n from here, then you can break this series up into, we can basically split it as k goes from 1 to j. And then the second one is as k goes from the j plus first term to the remainder, right? So you can break up the series into multiple series, okay? Let's see. And so then a series. So let a sub 1, a sub k, and beyond be an infinite sequence, right? So we have an infinite sequence. Then the sum of the first n terms of the sequence is called the nth partial sum of the sequence, and it's denoted by this, right? This is essentially what we were doing. So we have this infinite sequence, it just keeps going. And then we consider the first n terms, right? So we have the nth partial sum. So we add in the first term plus the second term plus the third term until we get to the nth term. And we can write it like this. This sum is a finite series. Finite meaning that it ends or terminates somewhere, right? Because we have an n. That's a finite series. So then it says the sum of all terms in the infinite sequence. So again, in the previous example, we added up the first n terms, right? We cut it off somewhere. And this one we want to consider, well, what if we add the entire thing? It's called an infinite series. So that's where we say we consider the first term plus the second plus the third plus the nth and beyond, right? So then now I is going from 1 to infinity of this series, right? So how do we add? So let's see what we can explore with infinite series, right? If we add them up infinitely. So let's see, write each sum in summation notation. Now these all truncated, they all stopped, right? There's no ellipses or anything on the back end. Let's see. So let's do it similar to how we did it before. Let's do like this. So notice that this is like our first term in the series. This is our second, this is our third, this is our nth. So nth, right? I was about to write full. Give me just a moment. Ooh. Are you burning anything? I don't know. Hang on, guys. I'm coming. I can't stop that because there's nothing's burning anywhere. I don't know why that's going on. Let me try to finish this out. I know we got an alarm going on. So we're almost there. Let me see if I can get this thing to stop. Oops, sorry. I don't know what's causing. What did you do to stop it? I think the battery's probably on that thing. Yeah, I don't know. It seemed like it made it. But it's so weird because like nobody's burning anything. It just, so it could be like carbon monoxide, I guess. Okay, sorry about that, guys. We made it through it. Let's see if you guys are still there. I think it's still going, so I'm just going to try to finish this out. All right. Let me check one other thing. Share the screen. Start the broadcast. Sorry, yeah, I didn't stop streaming because like I knew we were almost done. It was just weird because like nobody's burning anything. I was like, is that like carbon monoxide? But the other day I felt like I did smell gas, but there's no gas in here. Like that's the weird thing about it. So I was like, whatever. Okay. All right. So let's see. Right. So for instance, if n is 1, right? So it's almost like now. So these are like odd numbers, right? But instead of starting at 1, we're starting at 3. So it looks like we can capture each term. I think if we do like, what is it, 2n plus 1? So for instance, when n is 1, 2 plus 1 is 3. When n is 2, 2 times 2 is 4 plus 1 is 5. When n is 3, 6 plus 1 is 7. Is that what, 10? So we're doing 1 through 10. 10 times 2 is 20 plus 1, okay? So that captures each term, and then we want to capture adding these terms together. So that's where the summation notation comes into play. Okay. We're going to say, instead of n, I'm going to change it to like k, as k goes from 1 to 10. Right? I think this will be good. Okay, I think that's okay. So then if we look at the next one, this is like, let me see, this is our first term, our second, and then our nth. Okay. So if we say, what, if it were 1, that's like a 2, right? So we could do, there's a couple of ways we can do it. We could say like 1 plus 1, because that's like 2 squared. Instead of starting at 1, we could just start at 2. Right? We don't have to start it at 1. Like we can say sk, like if this was a 2. Let me see. That's what, 2 squared, 3 squared, and then 7 squared, right? So it looks like it's 1 over, it looks like it's 1 over k squared, right? But instead of starting k at 1, we're going to say as k goes from 2 to what, 7? So then 2 squared is 4, 3 squared is 9, 7 squared is 49, right? So we're going to go with this. I just did it that way so you can see that we don't necessarily have to start at 1. We can start at a different number other than 1. Okay, let's see, how do we do? And I want to say that there are other ways to write these. This is a sum of consecutive odd integers from 3 to 21. Each can be expressed as 2k plus 1, where k goes from 1 to 10. I think we got that same thing. We might just need some parentheses like this. Okay. And then this finite series is a sum of fractions, each of which has a numerator 1 and a denominator k squared, starting with k equals 2 and ending with k equals 7. I think we got that one. Okay, I think that brings us to the end of it, right? That's why I was like, I knew we were almost done. So I was like, it's okay. It's not a clean stream, but it's good enough for me. All right. So if there aren't any burning questions, or if you're still on the line, you know, I'm here. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.